I'd like to thank the organizers for the invitation to present my research today. I'm Madhu Khanna, Professor of Environmental Economics at the University of Illinois at Urbana-Champaign. My talk today is going to focus on applications and economics of artificial intelligence-based digital technologies for sustainable agricultural systems and their implications for policy. Agriculture across the world faces several grand challenges. Among these, a key challenge is meeting the growing demand for food and protein while adapting to climate change. Global food demand is expected to increase by 35 to 56% by 2050. So far, agricultural productivity has been increasing without increasing the use of inputs and land, mainly by increasing total factor productivity. But the focus of our agricultural sector has primarily been on increasing the supply of low-cost food. And in the process, agricultural production has been accompanied by large environmental damages. These damages have taken the form of chemical pollution of air and water. Irrigation water withdrawal and runoff is high. There is also increasing soil degradation in many parts of the world. And GHG emissions from fossil fuel use and land use change contribute a significant portion to total global emissions. Agriculture is also contributing to biodiversity loss. One of the key reasons for the impact of agriculture on the environment is because of excessive use of nitrogen per unit of cropland. And this is a problem that is occurring all over the world. Not only is the use of nitrogen more than what is actually required, but also the efficiency or the percentage of the applied nitrogen that is actually taken up by the plants is relatively low. Only 40 to 60% of the applied nitrogen is actually taken up by the plants, and the rest it takes the form of leaching or runoff and contaminates water. There's also significant human-induced soil degradation across the world, and this is leading to loss of soil productivity, loss of soil carbon stock, and to soil erosion being another contributor to water quality problems. So one mechanism to continue to increase yields without having a negative environmental impact is through a process of sustainable intensification. And sustainable intensification can be achieved through three key mechanisms. The first is by increasing input use efficiency so that more of the input that is applied is actually taken up by the plant and less is wasted as runoff. This requires addressing the vast spatial heterogeneity in soils and growing conditions at a fine spatial resolution that is prevalent across the agricultural landscape. There is also a possibility of substituting inputs, replacing chemical inputs with environmentally friendly inputs and technologies. And lastly, sustainable intensification can be achieved by redesigning agriculture, by building soil health through perennial cover and diversification of crops. Digital and precision farming technologies can play a role in this. These technologies take a variety of different forms. They range from from information technologies to computational technologies and farm machinery automation. And these technologies can enable data gathering, data analytics, as well as technology that can monitor the spatial variability and even auto steer equipment, apply inputs at varying rates, and so on. These technologies have been available for several decades. But their use and their effectiveness has been relatively limited. And so the question is, how can AI lead to sustainable intensification? And AI can essentially address two key problems that exist in modern agriculture and cannot be tackled by human labor or existing agricultural technologies alone. The first problem is determining the right amount of input at the right time and the right place. Even though we've had technologies that can apply inputs at variable rate, that can do soil testing and determine the variability in growing conditions, a key challenge is knowing how to respond to that variability and to determine what should be the variable rate of input application instead of applying inputs at this uniform rate. And this requires combining data from multiple sources on soil, weather conditions, prices, plant genetics, agronomy, and being able to make recommendations to farmers in real time at a fine spatial resolution. And this would be one mechanism for avoiding over application in some parts and under application in other parts, and thereby increase agricultural productivity while reducing input waste and pollution. However, this requires knowledge on how to respond to spatial variability in the field and not just the availability of precision farming equipment. A second problem is that human labor alone cannot monitor animals and plants at fine spatial resolution 24/7. And therefore, it cannot respond to the needs of plants as fast as would be beneficial in order to increase yields and prevent input waste. It is also not possible to remove weeds at scale without chemicals for most of the row crops that are grown on millions of acres. And lastly, it is not technologically possible for human labor alone to analyze soil health at scale and make recommendations for how to improve soil health. And so precision management of crops and animals can be improved through artificial intelligence technologies. And the way in which these technologies can actually do so is by not only gathering high resolution spatial data, but also analyzing that data and the growing conditions rapidly and using it for decision making. And so this data can be used to understand the causal mechanisms of how input applications and management practices affect outcomes, and thereby use this data to provide better recommendations and improve the ability to predict outcomes with certain management practices. And these technologies are also enabling autonomy and robotics that can make site-specific interventions on the field during the growing season. An example of such a technology is robotic weed management. And these small robots can go underneath the canopy of existing plants while they're still standing during the growing season and mechanically remove weeds without using chemicals, thereby reducing resistance and also reducing the labor intensity of managing weeds. So these weeding robots provide a low labor intensity, high efficiency, and an environmentally friendly solution. Another example is cover crop planting robots and drones. In the US Midwest, crop land and fields are left bare for almost 6 months, from November to April. And during that time, these fields are subject to soil erosion and nutrient leaching. So planting cover crops during the winter improves soil health and can prevent nutrient leaching and provide other ecosystem services, but it is costly, labor intensive, and time consuming. So robots and drones can plant these cover crops early in the season while the crop is still standing, and this improves cover crop establishment and efficiency. And as you can see from the pictures on the right, the typical approach to planting cover crops using a tractor leads to under-establishment of cover crops, whereas in the top panel we can see that these robots that plant these cover crops earlier in the growing season can actually improve the establishment of cover crops and lead to greater improvements in soil health. Additionally, there is a growing availability and development of the digital twin technology. Digital twin technology essentially provides a virtual representation of a farm, and by matching it exactly to the real farm, and it can thereby enable interventions to be experimented with on the virtual farm before they need to be tried out in reality, and therefore reducing the potential for errors and increasing the efficiency and accuracy with which these interventions can be practiced in order to increase profitability and potentially reduce environmental impacts. So this technology can improve understanding of how the farm functions and the effects of various interventions before they're tried out on the real farm. Additionally, generative AI has strong potential to provide advice to farmers on how to address various agricultural problems. And this is like a chat GPT. There's better advisory services that can be tailored to the needs of the farm. So the availability of AI technologies raises several issues. The first is which farmers are more likely to adopt these technologies? What are their barriers and motivations? Which technologies are more likely to be adopted? There's a whole suite of technologies that are available for different functions, and farmers have to choose which technologies, which components to adopt. Will these technologies actually improve environmental sustainability of agriculture? And what types of policies are needed to induce adoption of AI technologies to promote sustainability? There's a large literature that has been examining factors that influence adoption of modern technologies by farmers. And there's some key findings from this literature. The first is that profitability of the new technology compared to the old technology matters. And this depends on the effects of the new technology on cost of production and on yield. Technologies that have high fixed costs but can also lead to input savings, their adoption will depend upon the relative magnitudes of these components, and also how these components vary across growing conditions in a field, across fields, and so on. So some farmers may find it profitable to adopt a technology because of the growing conditions on their field, while others may not. Access to credit is another determinant because it can affect the ability of farmers to bear the upfront costs of investment in the new capital-intensive technologies. Risk of new technologies and their potential to either enhance risk or mitigate risk can affect farmers differently depending upon the extent to which the farmer is risk averse. And so the combination of risk aversion of the farmer as well as the riskiness of a technology can lead to differences in adoption behavior across farmers. Uncertainty about the impacts of a new technology on yield, on returns, and costs can create incentives to wait and watch before investing. Additionally, many technologies involve a trade-off between investments that are needed upfront and returns that may happen in the future. And so the discount rate of the farmer, or the rate at which the farmer is willing to trade off a dollar of investment today for a return tomorrow, will influence adoption behavior and again can vary across farmers. Access to markets for the availability of the new technology can also influence adoption across different locations that may differ in how much they can access, the accessibility of the technology. Education levels of the farmer, size of the farm are again other factors that influence the costs and the benefits of adoption. Across a range of different studies, we can generalize and say that typically the characteristics of farmers likely to adopt digital technologies are farm size, larger farm size, higher quality land, higher valued agriculture. Farmers that are using complementary technologies like computers, have access to high-speed broadband, are more likely to adopt AI technologies. Availability of skilled labor, as well as the relative advantages and perceptions about the usefulness of the technology can matter. And then farmer characteristics like education, attitudes towards the environment, the social norms in that region, and peer pressure are other factors that influence farmer behavior. There are many barriers to adoption of digital technologies, including the high costs, the need for demonstrated improvements. Additionally, the concern about loss of data confidentiality, ownership, and governance with AI technologies, where a lot of this data might be gathered just through the normal farm operations. Farmers may also be concerned about losing control on their farm management decisions and relegating that to an algorithm. Access to technical assistance, broadband technology can also influence adoption. Many farmers may view AI technology as a black box that they do not understand and therefore be reluctant to adopt. The rapid development of these technologies, potential for obsolescence, and operation of different components, how well they may operate with existing equipment, as well as limited rewards for providing ecosystem services, can limit incentives to adopt sustainable practices. So as we look across a range of different technology, we see some technologies have been adopted very rapidly. And mobile phones, for example, reached almost 100% adoption within a few years, even in many developing countries. On the other hand, access to the internet has been much slower to provide. Adoption of GPS technology has also grown very rapidly, and this is in part because it reduces the need for labor, it reduces labor fatigue, and it increases accuracy of operations to have GPS-based auto-guided equipment. On the other hand, adoption of variable rate technology, which can increase the accuracy with which nitrogen is applied across fields, and thereby provide environmental benefits, has been relatively slow in terms of its adoption rate. And adoption rates have also sort of plateaued around 20 to 30%. Adoption of robots and drones is just growing, and their robots are now being trialed across Europe and many other regions, including the US. And these are being now marketed by a growing number of companies. So there is a growing availability of commercial autonomous crop equipment, but many of the smaller robots are yet to be adopted at scale. Across other countries as well, we observe a similar pattern where there's been very rapid adoption of technologies like GPS, but much slower adoption of technologies that involve variable rate application. So, the question is, can AI lead to sustainable agriculture? And the availability of AI technologies alone does not guarantee that they will be adopted. Farmers are more likely to adopt technologies that increase yield, reduce labor costs, and increase profitability and provide private returns. But in some cases, actions that lead to private benefits can also benefit the environment. An example might be weeding robots that can increase yield and reduce labor costs and benefit the environment by reducing herbicide resistance and chemical pollution. But this is not necessarily the case for all technologies, and also not the case for all farmers. We find, for example, that farmers that are more forward-looking, that recognize that their decisions today have consequences tomorrow, that have low rates of discount, are more likely to adopt weeding robots. Also, if they have high levels of weed resistance, as compared to farmers that may have low levels of weed resistance, or maybe focusing on management decisions that are more myopic and have high rates of discount. Another challenge with inducing adoption of AI technologies is the non-point nature of agricultural pollution. In many cases, policy incentives are needed to induce adoption of environmentally friendly technologies that can provide environmental benefits, but impose costs on farmers or that have a negative impact on yields. However, a key challenge is designing cost-effective policy instruments, and that is because agricultural pollution is difficult to observe, measure, and monitor. And environmental damages from agriculture happen to be site-specific, farmer-specific, and therefore the same application of an input or the same practice does not have the same environmental impact. Therefore, because environmental impacts cannot be attributed to farmers, it is difficult to penalize farmers. And instead, the most environmental programs have typically tended to subsidize adoption of practices rather than basing these rewards or penalties on the performance or the amount of pollution that is being generated. And so these practice-based payments tend to be uniform across all farmers. They're not based on environmental impacts. They're not targeted towards where they can actually lead to the highest benefit of environmental improvements at lowest cost, and therefore they tend to be relatively ineffective. So designing effective policy incentives requires pricing inputs at their true social cost. so that those costs lead farmers to internalize the negative environmental impacts of input application decisions. Instead, very often inputs are subsidized in order to encourage more adoption and more use and increase yield. Additionally, these policy incentives need to be site-specific. They have to be targeted towards area where they lead to the largest environmental benefits at the lowest cost. They also need to mitigate risk with adoption. So, for example, providing insurance against downside risks may be needed in order to induce the adoption of technologies that may be perceived as risky. Policies that reduce upfront costs of investment by providing low interest credit can offset the high discount rates used by farmers to make investment decisions. And lastly, education and technical assistance by sources that are trusted by the farmers can impact their choices and incentives for adoption. So in sum, AI technologies can lead to sustainable agriculture by converting non-point source pollution into point source pollution problems. And that is because AI technologies can record the data, the management practices, and can then be used to assess what the impact of those practices is on the environment at a site-specific level. The many examples of these AI technologies that can lead to sustainable agriculture that we just talked about: precise fertilizer application, which can reduce nitrogen leaching and nitrous oxide emissions; robotic weeding, which can reduce the need for herbicides and lead to reduction in chemical pollution; lower cost autonomous cover crop planting robots that can improve soil health. And these improvements in productivity will in turn reduce the incentive to convert non-crop land into cropland and conserve land to meet the same amount of needs for food and fuel. But technology availability needs to be accompanied with appropriate policies and regulations in order to induce their adoption and to provide public benefits and not just benefits to farmers and developers. Thank you very much for your attention.